Welcome to Minimal Impact Design Standards Calculator Module 17, Infiltration BMPs. In this module, we're going to talk about the infiltration best management practices that are in the calculator. So we'll actually spend a fair amount of time outside of the calculator before we go in and show you some of those BMPs. I'm going to run the slideshow here so that it's larger. So in this module, we'll talk about which BMPs achieve infiltration, how the different infiltration practices work. We'll review the benefits and limitations of the different infiltration practices. We'll look at the supporting information in the Minnesota Stormwater Manual, and then just a quick couple examples in the calculator. So you could divide the best management practices that are in the calculator into three basic types. The first are the infiltration BMPs. These would be the BMPs that do not have an underdrain, so all water that's captured infiltrates into the soil below. You may see in some schematics that there is an underdrain, but it's shown at the top of the device. Everything that's captured is treated, is considered treated because it's removed from the stormwater treatment drain. Second type of practice are filtration best management practices. There is some infiltration in these BMPs below the underdrain, even if the underdrain is at the bottom. But most of the water in these practices is going to be captured by the underdrain after treatment and then returned into the stormwater treatment drain. The third type of practice are those BMPs that have no infiltration. These are going to be the wet ponds, constructed wetlands, sand filter, wet swale, and green roof. Note that the green roof, although it does not provide infiltration, does provide volume control. I'll touch on that just a little bit. But again, as with filtration BMPs, there is treatment that occurs in these types of practices. So if we look at the infiltration BMPs, these are the ones that can achieve the majority or your entire water quality volume or performance goal on A and B soils, and sometimes on C soils. Just a quick overview. These BMPs capture and store water, runoff water, and allow it to infiltrate into the underlying soil. So they're designed to capture a specific amount of water. That water may be ponded, as in a bioinfiltration device, or an infiltration basin or trench, or behind a check dam in a swale. Or the water may be stored in the media, as in a case of permeable pavement, or in a case of a tree trench. An underground infiltration may have water storage in the pipes and in the media surrounding the pipes. So all the water that's captured by this practice is going to infiltrate, and it must infiltrate within 48 hours to meet the drawdown requirement. Water that is not captured within this device simply bypasses the BMP and is not treated, unless it's treated by a downstream best management practice. There are other types of BMPs in the calculator that allow for infiltration. These are the disconnection, the harvest and irrigation practices in swales. These will infiltrate water over a vegetated surface. So they don't capture water and store it and allow it to infiltrate. They actually redistribute the water over a larger area. The water is applied over a vegetated area and allowed to infiltrate into the underlying soil. The volume of infiltration primarily depends on the size of the soil type for the vegetated area where the water is being applied. These BMPs can provide significant infiltration, but generally they're going to require larger areas to do so. And if there is a large enough area, they can be effective on C soils. So with a harvest and use system, for example, we'll capture the water in a pond or a tank and then distribute it over say a ball field or a golf course or something like that. It can be a very effective BMP if the receiving area is large. Impervious disconnection might be something like runoff from a roof being redistributed to a lawn. This is not quite as effective because the lawn itself is receiving rainfall directly, and therefore you have a limited amount of infiltration that can occur. In a swale without a check dam, the water is moving along a vegetated surface and it infiltrates as it moves along. Swales are generally not very effective at infiltrating water unless the underlying soils are very permeable you have a bioretention base, or the swale is very long, which creates greater contact time. This chart's a little busy. We'll walk through it fairly quickly, but it talks about the different infiltration practices and their ability to meet different criteria. So the ability to meet the water quality volume, as WQV, is high with infiltration trenches and basins and underground infiltration. These are practices that can be made fairly deep, and therefore you don't need as much surface area. If you have the available surface area, they can infiltrate large volumes of water. Underground infiltration, of course, can be put underground and therefore works in ultra-urban settings. Tree trenches are a highly effective practice too, because they can also be made fairly deep, and generally they're going to be underground, and therefore they can take up a large surface area underground without taking up surface area on the land surface. Bioinfiltration is rated as a moderately effective practice, primarily because its depth is limited to 1.5 feet to protect the vegetation in the system. Permeable pavement is considered to be moderately effective. The primary limitation there is the area that you have available for permeable pavement. If you have large areas available for permeable pavement, it's a very effective practice for infiltrating water. As I mentioned, harvest and reuse systems can be very effective if the receiving area is very large. Swales with check dams and disconnection tend to be less effective because the receiving area is smaller. Any of these practices that have manufactured media are going to be very effective in retaining pollutants. And so bioinfiltration, tree trench systems, and swales, harvest and use systems, and disconnection systems are all going to do a very good job of retaining pollutants. Permeable pavement and infiltration trenches are moderate, and underground infiltration typically is going to have low retention ability unless you do something to enhance it, like add organic matter. In ultra-urban settings, anything that's underground will be effective. That'd be an underground infiltration or a tree trench. Permeable pavement is also effective because it can be built in as part of the infrastructure. Most of the other practices are not particularly applicable in ultra-urban settings, especially those that need surface area to infiltrate the water. Infiltration trenches and basins can be somewhat effective if you have A-type soils where you can make this practice deeper as opposed to taking up a larger surface area. Multiple green infrastructure benefits are good for tree-based systems and for harvest and use systems and disconnection systems. By multiple green infrastructure benefits, we're talking about things like habitat improvement, energy savings can be built in along with transportation corridors, and those types of things. Some of the practices, infiltration trenches and basins and underground infiltration, have low green infrastructure benefits unless you incorporate vegetation into them, in which case their value increases. The ability to meet the water quality volume on sea soils is typically low unless you have a large surface area to apply the water over, and that would be a harvest and reuse system. Let's just say you're capturing water and you're applying it over a ball field or a golf course. You have a lot of surface area that you can, even on fairly low infiltrating soils, the surface area is so large that you can infiltrate a large amount of water. So how is infiltration achieved for BMPs that capture water and have an underdrain? So as I said, the water is filtered in these. You're treating them for phosphorus, sediment, metals, organic materials. Most of that water is going to be captured by the underdrain and returned to the system after it's been treated. But any water that's below the underdrain will infiltrate into the underlying soil. If you raise the underdrain, as shown in these diagrams here, you can increase the amount of infiltration because the water that's stored beneath the underdrain will eventually infiltrate. Even with a raised underdrain, you're typically going to achieve less than 40%. In fact, generally less than 20% of the water quality volume with these BMPs. And these are going to be used typically on your C and D soils. These BMPs can retain water through means other than infiltration. Green roof can capture and store water, and it will be taken up by the plants or evaporated directly from the soil, the media that's on the green roof. So you do get some capture there. Harvest and reuse systems, water can be used for non-irrigation purposes. You can use it for toilet flushing, for example. Pre-trench and bioretention systems in the calculator are going to get credit, even though you have some infiltration in these systems. You'll also get credit if you have trees, which you will in a tree trench system, but if you put trees in your bioretention system, you'll also get evapotranspiration credit. So you're getting some additional water quality volume control there. Supporting information in the manual, there's 3 basic pages that have good information. There's information throughout the manual on infiltration, but these 3 websites in particular focus on stormwater infiltration. This first one here provides BMPs for stormwater infiltration, and it walks you through each of the best management practices that allow for infiltration, infiltration trench, bioinfiltration, permeable pavement, and so on. You'll see that each one of these contains information on where it's applicable and how effective it is at treatment, and it provides several links within the manual related to that best management practice. And for each one of these BMPs, you see a similar type of a format. I'm going to bounce back and forth here for just a bit. Get the right slide here. It's always a good idea. The second link here will take you to this page, which is Stormwater Infiltration Best Management Practices, and you'll see a portal here to permeable pavement, tree trench, bioretention, and so forth. If you were to go to one of those pages, say infiltration, you would see that this is where you would find information, the overview, types, design, construction, operation, maintenance, and so forth, including case studies and links to the MIDS calculator. And this third site provides other information on stormwater infiltration, including links to the portal that we just looked at, some information on water quality, surface water, groundwater quality impacts from stormwater infiltration, information on constraints such as karst settings, shallow groundwater, contaminated soils, and groundwater, and then some other information, including links. So we'll briefly go into the calculator. I'm not going to go through any actual exercises here. You can go to each of the individual BMP videos to do that. I click on the MIDS calculator link here. I'm going to create a new file, and let's just call it infiltration. And we'll open that up. And if you've seen any of the other videos, you remember that you need to have 3 inputs. Here you need to answer the question yes or no, whether it's complying with a construction stormwater permit. You need a zip code, 55155 is where I'm at. That will provide you with the rainfall data. And then you need some impervious surface. I'm just going to put 5 acres in here for now to give me some water quality volume that I need to control. Again, this information, the other information is optional, and you can change the default values for phosphorus, TSS, and your retention requirement. With this now, we can go into the schematic tab, and we'll take a look here and we'll see where our infiltration practices are. Again, here's the bioretention without an underdrain, bioretention with an underdrain, so we're primarily interested in the bioretention, bioinfiltration, we call it in the manual, without an underdrain. Infiltration trench or infiltration basin is another BMP. Infiltration BMP. Underground infiltration is another best management practice. Infiltration practice. Permeable pavement is another infiltration practice. I'm going to align these so I can get everything in there. Again, tree trench, you have tree trench without an underdrain, with an underdrain. The pure infiltration practice is without an underdrain. I'm going to drop swale main channel on there because you can put a check dam in that system. Harvest and use BMP, and the disconnection BMP. So these are the primary infiltration best management practices. Most of them are formatted fairly similar. Like I said, the best way to find out about each one of these is to actually go into the video on each specific BMP, but let's just quickly open up the bioretention, bioinfiltration practice. Let's route 1 acre to this, and this is going to be a standard approach. So you're going to have water ponded in this particular BMP. So to meet the water quality volume, we need to size this so that we can capture that much volume. And the simplest way to do that is to put in a system that's 1 foot deep, and it has to be on a soil that's going to allow infiltration during the drawdown period of 48 hours, and you'll see that this BMP meets the infiltration requirement. All the TSS, you go to the BMP summary, we're meeting our performance goal, and we're getting 92% of the annual volume captured, which means we're going to get 92% of the phosphorus and TSS captured also. I had mentioned in the table that there are some restrictions for bioinfiltration. For example, if I wanted to put 2 feet in, it's not going to let me do that because I'm restricted to 1.5 feet for this BMP. I don't have that restriction in either the infiltration basin or the underground infiltration or in the tree trench system or in the permeable pavement. These 4 BMPs, you do not have that depth restriction, and therefore they're going to be more effective, particularly if on A-type soils where you can make your system deeper as opposed to larger at the surface. Just very quickly, I'll go into the swale. I'm not going to route any impervious to it, but I'll just show you that you can see that you have information here that you can enter regarding your check dam, so you can size your check dam. The bigger you can make your check dam, the more water you can store behind it, the more effective this best management practice is going to be for infiltration. These are the 2 BMPs that I talked about that will require you to capture water or route the water over vegetated surfaces. The soil would be the same way if you did not have check dams in it. So in these systems, the water is being applied to vegetated surfaces, just simply allowed to infiltrate that way. These other BMPs that allow for some infiltration are going to be the ones that have an underdrain, biofiltration, tree trench. Permeable pavement is the same BMP. This one's a little different than the other 2. It's the same BMP, but you can put your underdrain in the permeable pavement in different places, and then a swale with an underdrain. So each of these BMPs will have water infiltrating below the underdrain. If you raise an underdrain, you allow for storage above it. So let's just go to bioretention, for example. And it will ask me, am I raising the underdrain? And let's just say no for now. And you can see there's a lot of inputs here. This is not a line system. I'm just going to put some numbers in here real quickly. 3993 again. And let's make the bottom surface area the same. And so this is the underdrain is at the bottom here. The depth isn't going to matter because most of the water is going to get captured by the underdrain, and it will drain in 48 hours. So the depth is not particularly, my apologies, 1.5 again for the ponded depth. That's for to protect the vegetation. It's the media depth that's not relevant here. So you can make it thicker if you'd like. I'm going to put in some other numbers here for the porosity and the field capacity. And we're not going to put a tree in this system. We'll use mixed seed. No amendments. And let's put sea soil underneath this. And it needs to drain in 48 hours, which is not a problem because of the underdrain. And so let's look at our volumes here. And you can see that we're not getting anything underneath the underdrain. We're getting 958 cubic feet from below the underdrain. So that's water that's infiltrating while this entire system drains down. if we were to go back and put in an underdrain, and let's put that underdrain 0.8 feet, which would be the maximum you could do for a sea soil. And then let's go down and take a look, and we'll see now that we're getting 800 cubic feet of water infiltrating that was stored below that underdrain. So we're getting about double what we had before because we raised the underdrain. Maximize this again. So that was a very quick overview of the infiltration BMPs. I would suggest that you look at the other videos that relate to these particular practices. The infiltration, underground infiltration, bioinfiltration, they all have their own modules. Or you can view any of the other calculator modules by going, if you're in the manual, by typing in MIDS calculator videos in the search box, or by going to this link here. That ends Module 17, Infiltration Best Management Practices.